The early days of air transport proved a simple point. For safe and profitable flights across the oceans, the aircraft of the day were nowhere near big enough. The push to build the first giant flying boat came from the economics of air travel. The thinking at the time was that passenger service could only turn a profit by carrying large numbers of people at once, just like with other forms of transportation. And for those flights to attract more passengers, which were in short supply, travelers needed better safety, more space, and more comfort. These demands drove aircraft to grow larger. On top of that, it was critical to significantly increase payload capacity. The real breakthrough in flying boat development was a dramatic leap in payload capacity. Everything needed for long-distance flights, relief crews, navigation instruments, water maneuvering equipment, radio stations, and so on, ate up such a huge share of a small aircraft's payload that carrying any significant amount of cargo was simply impossible. The larger the aircraft, the less of its payload was eaten up by all that equipment. After years of research and preparation starting in 1924, construction of the flying boat started in December 1927 at the new Dornier AG facility in Altenrhein, Switzerland. The first flight took place on July 12, 1929. Every previous attempt to build a giant aircraft had ended in failure, and none of those planes even came close to the Do-X in size. That tells you just how many challenges had to be overcome, how much research had to be done, how many years of hands-on experience it took to find a new path forward. All of that laid the groundwork for designing the Do-X. To achieve the goals they had set, the team decided to rely only on proven engineering solutions. Since its founding, Dornier Werke had been building large, seagoing flying boats. For years, the company focused on experimental and developmental work, methodically advancing the art of all-metal aircraft construction. Between 1914 and 1918, work began on a series of fundamental innovations. Most of them were aimed at creating aircraft built primarily from metal. The first seaplane, built in 1914, had a wingspan of 143 feet. The four-engine RS-3, built in 1917, became the first large seaplane to meet the German Navy's seaworthiness requirements. The most important innovations used in Dornier flying boats, and later in the Do-X, had already been developed and tested. These included Dornier's pioneering use of light alloys and steel for primary structures, semi-cantilever wings, the monoplane configuration, tandem engine placement, and sponsons mounted on the flying boat's hull. After development of large aircraft was halted in 1918, a series of smaller seaplanes were built between 1919 and 1924. Among them were the Libelle and the twin-engine Dornier Wal flying boat, which at the time was the most successful and widely used flying boat in the world. In 1926 and 1927, the Superwal was built, a flying boat powered by 4 engines with a combined 2,000 horsepower. It surpassed the World War I era flying boats in both takeoff weight and engine power. All 28 of these projects and the experience gained from them made it possible to begin building a flying boat that far exceeded anything that had come before in both size and power. The Do-X flying boat was a monoplane with semi-cantilever wings. The wing panels were attached to each side of the hull and supported by 3 diagonal struts, also anchored to the hull. The tail assembly was mounted on a raised tail section. Power came from 12 air-cooled engines mounted in 6 nacelles above the wing. For structural rigidity, the nacelles were linked by a small auxiliary wing. The construction was typical of Dornier aircraft. Special duralumin profiles combined with smooth sheet metal skin and high-grade steel produced exceptionally strong structural components. The large size of the aircraft meant that drawn profiles were replaced with special pressed duralumin profiles to handle the heavier loads. The wing skin near the engine nacelles was duralumin. Elsewhere, it was fabric. The hull had a sharp bow with an angled stem and tapered frames that transitioned into a flat bottom. Above the sharpened junction between the bottom and the vertical walls, the hull sides had a slight tumble home. The bottom of the hull featured a transverse step to aid takeoff. Earlier Dornier boats used proven longitudinal steps, known as Längsstufung. This meant that when moving across the water at high speed, only the narrow lower section of the step was in contact with the water, not the wider upper portion. Wave impacts during takeoff runs had less effect on the hull. The flat middle portion of the transverse step was positioned about 28 inches ahead of the curved side sections. Behind the step, the lower hull was raised well above the water, protecting the tail assembly from wave impacts. To ensure good landing characteristics and water maneuverability, a keel-shaped displacement float was placed behind the step. At its end was a rudder for steering the boat on the water. Along the sides of the hull, sponsons were fitted for stability, the same type used on other Dornier flying boats. The overall length of the hull was 131 feet 5 inches. The width of the hull, including the sponsons, was 32 feet 10 inches. The hull body averaged 11 feet 6 inches wide and stood 21 feet tall. Empty, it drew just 2 feet 7 inches of water, rising to 3 feet 5 inches at a loaded weight of 110,230 pounds. The metacentric height at a weight of 110,230 pounds was 15 feet. The hull, together with its sponsons, had a volume of 14,126 cubic feet. The cross-sectional area at the main frame was 185 square feet. The frame spacing was 28 inches. There were 58 transverse frames in the hull altogether. One notable new feature was a keel beam measuring 6 feet 11 inches in height and 76 feet 5 inches in length. This beam ran from the bow to the step and provided substantial rigidity to the hull. To the left and right of the keel beam, at distances of 3 feet and 5 feet 2 inches respectively, were keelsons. Combined with the transverse frames, this created a very strong structural framework. In the area of the hull bottom that endured heavy loads during takeoff runs, strong load-bearing metal sheets crossed over the transverse and longitudinal frames. They divided the framework into small sections to which the skin, approximately 22 square feet in area, was attached. Where the sponsons met the hull, the junction was rounded. This new sponson arrangement offered both static and hydrodynamic advantages. The overall length of the sponsons at the root was significantly greater, allowing for a more rigid load-bearing structure. Thanks to this curved shape, water was deflected away from the hull during takeoff. To put this in perspective, the hull weight per cubic foot of volume in the small Libelle boat was 1.87 pounds. In the larger seagoing wall boat, this figure was 1.64 pounds. In the Do-X, it was just 1.31 pounds. Under the same loads, the structural stresses in the Do-X were much lower than in smaller boats. In small boats, with their thin skins and profiles, the risk of localized buckling and deformation was much higher. What's more, the Do-X had lower localized stress levels. The compartment layout was completely different from earlier flying boats and more closely resembled that of a ship. The large dimensions allowed the hull to be divided into multiple decks. The hull itself terminated at the main deck, which sat 4 feet above the waterline. 8 transverse bulkheads divided the hull into 9 compartments. Each sponson was also divided into 4 separate watertight compartments. This meant the boat would stay stable even if 2 compartments flooded. The displacement of each sponson was 1,536 cubic feet. The spaces on the main deck weren't constrained by the watertight bulkheads below and could be reconfigured as needed. On the upper deck above, all the spaces needed to operate the aircraft were located. The pilot's cockpit, the captain's and navigator's compartments, a dedicated engine control room, a radio room, and an auxiliary engine room. The enclosed sections of the upper deck began behind a long, curved fairing and ended at the trailing edge of the wing. The cockpit and navigator's compartment offered excellent visibility. The remaining compartments were located inside the wing, where it passed through the hull. Thanks to the compartment layout on the main deck, it was possible, unlike in smaller flying boats, to use them to increase the hull's rigidity. The wing had a rectangular planform with slightly rounded tips. The wingspan was 157 feet 6 inches and the chord was 31 feet 2 inches. The total wing area, including the ailerons and the upper wing, was 5,225 square feet. At a takeoff weight of 114,640 pounds, the wing dimensions met the DVL standards for passenger aircraft. The center spar was located roughly at the point of maximum wing thickness. The front and rear spars were placed far apart. The distance from each of these spars to the center spar was 9 feet 2 inches. The distance between the transverse beams reached 11 feet 10 inches. The spar caps were made from pressed duralumin angles, similar to bridge construction techniques. Depending on the bending moment, additional fasteners could be installed. Where the flanges were lighter, vertical angle braces were added to maintain strength while saving weight. The front and rear spars were structurally identical to the center spar. The transverse structural members of the wing were also made from pressed profiles. Where they met the front spar, it was sometimes necessary to install a frame so crew could pass through the wing. The transverse structural members, spaced between 9 feet 2 inches and 11 feet 10 inches apart, together with the 3 spars formed wing sections. Thanks to their bending rigidity, they combined with the outer skin of thin metal sheets or fabric to form what were called primary wing skin sections. The portion of the wing behind the rear spar was built as a separate trailing edge panel. The leading edge of the wing was entirely metal and attached to the front spar. The main wing surface, as already mentioned, was partly covered with thin metal skin and partly fabric. This design was simple and cheap to build. Bolted to mounting nodes inside the main load-bearing deck of the hull, the wing panels were secured in place. Although the wing wasn't particularly thick in profile, the internal depth was enough that crew members could actually walk through much of it. The maximum wing thickness was 4 feet 2 inches. The upper wing served to ensure the overall rigidity of the elements to which the power plants were mounted and was made entirely of metal. The upper wing was not intended to reduce the load on the main engine mounts. To prevent extra stress on the primary structure, the outer engine nacelles were connected to the upper wing at its tips and center section. The engine mounting structures featured a special lattice design with fairings. To provide access to the engines, large doors were installed on both sides of the hull. Flight controls and tail assembly. The ailerons were positioned on the trailing edge of the wing near the tips and were equipped with aerodynamic balance surfaces. The horizontal tail consisted of small stabilizers fixed to the tail section of the hull, and larger main stabilizers mounted above them. At the ends of the main stabilizers were the elevators, also balanced by special surfaces. The vertical tail consisted of a fixed fin with 3 rudders. The center rudder was mounted on the fin. The 2 side rudders were designed as balanced units positioned between the stabilizers. The pivot axes were offset rearward so that they also reduced the load on the center rudder. The rudders were actuated by rods connected to the pilot's pedals. All control system mounting points and actuators used ball bearings. This meant that operating the control surfaces required very little effort. To balance out the loads that arose, trim tabs were used. They compensated for both longitudinal and lateral loads. Trimming was done by adjusting the angle of attack of the corresponding balance surface. This required no effort and could be done right from the pilot's seat. The total area of all horizontal tail surfaces was 575 square feet. The total area of the vertical tail surfaces was 204 square feet. All control surfaces had trim tabs to balance the forces acting on them. The distance from the elevator to the water surface was 20 feet. To protect the side rudders from wave impacts, the hull was extended rearward. Power plant. The flying boat was powered by 12 Siemens Jupiter air-cooled radial engines, each rated at 525 horsepower. Engines from other manufacturers of similar weight and power could be installed as alternatives. The engines were arranged in tandem in 6 nacelles. The tandem arrangement was a necessity given the large number of engines. By the time the Do-X was built, tandem engine configurations with all their pros and cons had been in use for over a decade. This arrangement was the simplest, lightest, and most reliable, and it was becoming increasingly common. The tandem arrangement, or twin engine setup, cut engine installations in half. 2 9-cylinder engines in tandem were no more complex than a single 18-cylinder engine, and it was considerably more reliable in service. First, a smaller engine is more reliable than a larger one. Second, if an engine, gearbox, or propeller failed, only half the power of the twin engine was lost. The air resistance of a nacelle housing such a twin engine was no greater than that of a nacelle with a single large engine. A twin-engine nacelle could use smaller diameter propellers while maintaining the same efficiency. The same was true for blade tip speed at equal RPM. One engine in each nacelle drove a tractor propeller while the other drove a pusher. The propellers were geared down at a 2-to-1 ratio. Equally important, the entire power plant was much easier to access and service. Through passages inside the wing, maintenance crews could reach the teardrop-shaped fairings in the lower part of each nacelle. All lines and connections, right up to where they met the engines, were accessible during flight. Even if an engine shut down in the air, it could be inspected and repaired. The fuel system also relied on time-tested designs. Fuel was stored in 4 cylindrical tanks, holding 793 gallons each, 2 tanks holding 449 gallons each, and 2 small wing tanks holding 79 gallons each, for a total of 4,227 gallons. The fuel tanks were located in the bottom of the hull. They were connected to a collection tank from which pumps delivered fuel to 2 79-gallon tanks in the forward section of the wing. As a backup for fuel delivery to the engines, 3 additional methods were available: a ram air pump, an electric pump, and a manual hand pump. Fuel from the wing tanks was pumped to the carburetors. Excess fuel was drained into a collection tank. On the upper deck, an observation window allowed the crew to monitor fuel flow. The entire fuel line system was accessible for inspection and repair during flight. The oil tanks held a total of 423 gallons. Each engine nacelle contained an oil tank holding 26 gallons. The hull housed a main tank holding 264 gallons. For engine monitoring and maintenance, an entirely new approach was adopted. The size and number of individually mounted engines made it impossible for the pilot to manage all the engines alone, as had been standard practice. A dedicated engine control room behind the captain's compartment housed all the monitoring equipment and switches. A flight engineer was stationed in this control room at all times. All the gauges and switches for engine management were arranged on panels along both side walls. The control room also contained the entrances to the passageways leading to all the engines housed in the wing. Since the pilot still needed to regulate engine power on an aircraft this size, the throttle levers for each of the 6 engines on one side were located inside the wing. These were linked to the engine control room and to 2 master levers in front of the pilot. This way, the pilot only operated 2 throttle levers, one for the starboard engines, one for the port engines. So the pilot could monitor engine power at a glance. 2 master tachometers were provided. They displayed the average RPM of all 6 engines on their respective side. If the engineer disconnected any engine from the master control, a red warning light automatically lit up in the cockpit. The crew started the engines with compressed air from the engine control room. The flight controls were conventional. Directional control was handled through pedals. Pitch and roll control was managed through a control wheel mounted on the control column. The aerodynamic balance surfaces were designed so that one pilot could fly the aircraft without significant effort. The pilot could adjust the pitch trim from the seat using a handwheel that changed the elevator trim tab setting. To level the aircraft in case of engine failure, the rudder trim could be adjusted the same way. Another large handwheel beside the pilot operated the water rudder. Control forces were mostly transmitted through push rods and bell cranks. All control linkage components ran on ball bearings. Every element of the control system was easily accessible. The size of the flying boat allowed it to be equipped with every navigational aid known at the time. The equipment configuration could be changed depending on the customer's wishes and the aircraft's intended use, so there was no single standard. The cockpit had the standard instruments of the era: airspeed indicator, altimeter, artificial horizon, rate of climb indicator, and compass. The captain's and navigator's compartments included chart cabinets and a work table, a compass, signaling devices, and communication equipment for speaking with the engineers, the pilot, and for contact with ground stations, other aircraft, and ships. Also present were a drift sight for measuring wind drift and an echo sounder. The radio room behind the engine control room held all the necessary modern wireless communication equipment and a radio direction finder. In the auxiliary engine room, a 12-horsepower DKW water-cooled engine powered the starting air compressor, the radio and lighting generator, and a pump. The equipment needed for water operations included a heavy sea anchor weighing about 220 pounds, a cable drum with line and hawse hole mounted above the stem. Additional gear included a sea drogue, hull damage repair materials such as patches and bilge pumps, inflatable boats, towing lines, boat hooks, and everything else a seagoing vessel needs. The main deck offered generous passenger accommodations. The total length of these spaces was 79 feet, with an average width of 10 feet. Depending on the route length, the cabin could seat up to 100 passengers. For the first boat, the compartment layout was as follows. Immediately behind the bow collision bulkhead, which served as protection in case of a water collision, were a bar, a smoking lounge, and small sitting rooms. Amidships was a large compartment about 23 feet long and 11 feet 6 inches wide. Further aft toward the stern were several small cabins for 8 people each, sleeping quarters, an electric galley, and washrooms with showers. Today, few people realize how primitive cockpits were at the dawn of aviation. Less than 20 years had passed since pilots first sat on a small seat with their feet on the control pedals and their hands on a control wheel. Mounted on the struts of this flying machine were a throttle lever and a fuse box. There were no other instruments, nothing to monitor flight conditions or engine performance. If a pilot wanted additional flight data, the altimeter had to be hung around the neck. There was simply nowhere in the cockpit to mount it within the pilot's view. As aviation advanced and aircraft grew larger, the demands on pilot accommodations and on the navigation and monitoring equipment that ensured safer flights kept growing. If you compare the cockpit of those early aircraft with the cockpit of the Do-X, the difference is roughly the same as between a fishing boat's wheelhouse and the bridge of the ocean liner Bremen. From the navigation compartment, the clean, simple layout of the cockpit was immediately apparent. Some of the gauges and switches that regulated the power plant, unlike in earlier aircraft, were not placed in front of the pilot. This meant the pilot had fewer things to manage than in small twin-engine boats. The pilot could focus on what mattered most, flying the boat and watching the course and weather. This simplification was possible because of the dedicated engine control room on board, where all the gauges and controls for every engine were centralized. From this control room, where a trained specialist was always on duty, all engines were started using compressed air cylinders. After a warm-up and performance check, engine control was switched to 2 levers in the cockpit. Each lever controlled the throttle across all power ranges for all 6 engines on one side. This freed the pilot from having to monitor all power plant parameters. A single tachometer shared by the engines on each side showed the pilot the average RPM of all 6 engines. From that reading, the pilot knew how much power the engines were producing. If any of the 6 engines linked to that lever shut down for any reason, a red warning light lit up in the cockpit. In practice, this division of duties meant the pilot's job wasn't all that different from flying other aircraft. The cockpit had dual controls. Pitch control, as usual, was handled by a wheel on the control column. Directional control was through pedals. The cockpit was very spacious and well protected from the elements. Large glass panels gave the pilot excellent visibility. In addition to the main controls, photographs show handwheels beside the left seat. 2 small handwheels were used to adjust the trim tab settings for the rudder and elevator. This allowed the pilot to fly the aircraft without fighting the controls, even as the aircraft's weight or flight conditions changed. With the controls released, the aircraft would continue flying steadily on its own. This was especially important for the rudder. If engines on one side failed, the resulting course deviation could be corrected without touching the rudder pedals. The flight instruments were mounted on a panel beneath the cockpit ceiling. This kept them out of the pilot's line of sight while still being easy to read. For engine monitoring, all the relevant gauges were relocated to the engine control room inside the main wing behind the navigator's station. This particularly important control room has already been described. Communication links were provided between the engine control room and the cockpit. The captain's compartment, positioned between the engine control room and the cockpit, allowed the boat's captain to stay in contact with both the pilots and the control room. Despite the separation of the various stations, this setup made it easy to manage the boat and keep tabs on all the instruments. To start the 12 engines, an auxiliary power plant was located on the upper deck behind the radio room. It consisted of a 12-horsepower, 2-stroke water-cooled engine. Through a clutch, it drove an intermediate shaft. This shaft carried V-belt pulleys, some with double grooves. Depending on the need, this shaft could drive a 2-cylinder air compressor, an electrical generator, a fuel pump, and either a radio generator or a generator to supply power to the galley. Compressed air first passed through a multi-purpose valve that injected fuel into the engine's intake manifold, where a special device atomized the fuel in precise amounts. Then, through a second multi-purpose valve, compressed air at 170 to 220 pounds per square inch was fed to the engine being started. The engine turned over, high-voltage electrical current was supplied from the auxiliary power plant, and the engine fired up. Under normal conditions, starting all 12 engines took 3 to 4 minutes. The compressor could produce enough air to start 2 engines at once if needed, 1 on each side. Each engine's throttle was controlled by a single lever. Throttle control for all 6 engines on one side was managed through a common shaft. Individual engines could be disconnected from the shared control system. As soon as any engine was shut down for whatever reason, a warning light lit up between the pilots in the cockpit. The average RPM of the engines connected to the shaft on each side was displayed on a tachometer. The pilots always knew how many engines were running and what average RPM they were producing. Naturally, the flight engineer would only disconnect an engine under exceptional circumstances and had to immediately notify the pilot. The pilot controlled the throttle shafts using two side-by-side levers, which were connected through push rods to the hand wheels described earlier. Both levers had to be moved by the same amount. In simple terms, all engines operated at the same settings during normal flight. For special maneuvers, turns or maneuvering on the water, the pilot could increase the RPM of just one engine group. Then both levers were returned to equal settings. Switching the ignition timing between advance and retard was done with a small rotary handle located below the clutch lever. It had only two positions. For engine starting, retard timing was needed. Once the engine started, the timing was switched to advance. After starting, each engine could be monitored through the gauges in the engine control room. Above each engine's control lever was a row of instruments: an electric tachometer, an electric thermometer for oil temperature before the engine, an electric thermometer for oil temperature after the engine, a warning light that came on if oil temperature exceeded the limit, an oil pressure gauge for the lubrication system, and a fuel delivery pressure gauge. The electric thermometers could be switched on and off with a small toggle. On the lower part of the panel were the previously described clutch engagement levers with signal light contacts, ignition regulators, and the engine start and shutdown controls. To prevent accidental engagement, a safety lever was positioned in front of the clutch lever. To relieve pressure on the fuel system gauge when the boat was stationary, a small valve was provided on the front of the instrument cabinet. In front of the passage to the radio room was the main electrical distribution cabinet for the entire power supply system. It housed current and voltage meters, insulation testing equipment, main lighting switches, and the primary fuses for the power supply system. Smaller fuse and switch cabinets for the lower and intermediate decks were located where they were needed. Only engine instruments were placed in the cockpit. The pilot could monitor engine RPM and know how many engines were operational. These instruments were also provided for the co-pilot, whose station was in the same cockpit. The cockpit was equipped with a compass, altimeter, airspeed indicator, rate of climb indicator, pitch and roll attitude indicators, and a heading indicator. These last instruments were shared with the course plotting equipment in the navigator station behind the cockpit. In addition to those instruments, there was a variometer and a ship's clock. A radio direction finder and echo sounder were used to determine the aircraft's position in poor visibility. In case of a sudden power failure in the onboard electrical system and the engine shutdown that would follow, both pilots had easy access to a tamper-proof master circuit breaker. In the navigator station, there was a large compass, an altimeter, and a clock. Communication between the navigator station, the radio room, and the cockpit was handled by electric intercoms, pneumatic message tubes, and speaking tubes. There was a simple light signaling system with red, white, and green lamps. It provided information about the status of engines in each nacelle. To further improve flight safety and keep track of the gauges and mechanisms spread across the engine nacelles, where they met the crew passageways, each engine had a convenient set of instruments: a mechanical tachometer, an oil pressure gauge, a fuel pressure gauge, and an oil temperature thermometer. All these instruments had quality electrical lighting for easy reading during night flights. Even today, in an age of supersonic jets and space travel, the Dornier Do-X remains a fascinating chapter in aviation history as one of the largest flying boats ever built. With Do-X model kits now available to aviation enthusiasts, interest in this remarkable aircraft continues. What follows draws on original period documents, including a report by Dr. Claude Dornier himself. Among the surviving materials is an original report by the Do-X's creator, Dr. Claude Dornier, published in 1930 in both specialized journals and the general press. The report covered the creation of the Do-X and its technical details. A report covering the Do-X flight tests from July 12, 1929 through late August 1931 was published in the December 1931 issue of Die Luftwacht magazine Airwatch. It was distributed as a special Dornier Company publication. There are also numerous photographs from that period sourced from the special Die Luftwacht edition. Test flights of the Do-X from July 12, 1929 through the end of August 1931. By the time the Do-X arrived in New York, the planned test flights and development program had been completed ahead of schedule. Interest in the world's largest flying boat was enormous everywhere, and opinions about this radical new design were sharply divided, so the full story of the aircraft deserves to be told, including the various tests conducted by Dornier together with the airliner's owner. These tests can be divided into 5 separate periods, none of which aimed at setting any records. The only requirement was to conduct thorough technical and maritime flight tests under a variety of conditions. Trial flights on Lake Constance with Siemens Jupiter engines, trial flights on Lake Constance with Curtiss Conqueror engines, demonstration flights across Europe from Lake Constance to Lisbon, trial flights off the coast of Africa, Lisbon, Las Palmas, Villa Cisneros, Bolama, Boubaké, a maximum range ferry flight along the route Bolama, Cape Verde, Natal, Rio de Janeiro, a maximum range flight with passengers and mail along the route South America, West Indies, North America from Rio to New York. The long-term research and trial flight program from the start of flights on July 12, 1929 through November 1, 1930 included taxi trials, maneuvering, and stability tests on the water, takeoffs and aircraft demonstrations by factory test pilots, night flights performed by pilots from the German Aviation Test Center, DVL, prototype testing and certification for regular flight operations, takeoffs with a new crew, specialists, check flights, and measurement flights under all weather conditions. The flights of the first test period showed that the rated power of the German Siemens Jupiter engines was insufficient for flights at normal payload. These engines produced a maximum of about 480 horsepower. Sustaining even 410 horsepower would chronically overstress them. It was therefore decided to fit the aircraft with more powerful engines. Due to post-World War I treaty restrictions on German aviation engine production, no engines above 500 horsepower were available domestically. The decision was made to use American Curtiss Conqueror water-cooled engines, which were readily available. Swapping the engines required new nacelles, radiators, oil coolers, and more. This work was completed in early August 1930. The first flight with the new engines took place on August 4, 1930. The test flight confirmed improved performance, and there was no need for another long period of test flights on Lake Constance. After 35 more flights, it was decided to take the Do-X abroad. On November 3, 1930, the second phase of the program began, a demonstration flight across Europe from Lake Constance to Lisbon. Despite the poor late autumn weather, the flight went off without a hitch. At each stop, the team paused for 2 to 3 days. This time was used for aircraft inspections and local demonstration flights to familiarize foreign specialists with the aircraft. From Lisbon, the Do-X was to fly to the Cadiz aircraft factory, Construcciones Aeronáuticas S.A. There, preparations would be made for the second route, Cadiz, the Azores, Bermuda, New York. The engines were to be inspected, excess cargo offloaded, and the crew roster finalized. In Lisbon, while preparing for the next leg to Cadiz, departure was scheduled for the morning of November 30th. Everything was ready. But on November 29th at 2:30 in the afternoon, a fire suddenly broke out on the aircraft while it was moored to a buoy. The flames destroyed the entire fabric covering of the left wing. The fire started in the wing on a canvas cover that had been spread out to dry. The auxiliary 12-horsepower DKW engine, used for battery charging, and had been running intermittently. A gust of wind blew its exhaust onto the cover, heating it to a dangerous temperature. Although the combined efforts of the crew and a group of Portuguese naval specialists managed to extinguish the fire, repairs had to be carried out on site over the course of 6 weeks. Though the repair itself was straightforward, the Do-X's complex wing structure made the work slow. The repair materials arrived from the factory 6 weeks later. From January 24th to 28th, 1931, test flights were conducted at various loads. Takeoff weight reached 120,150 pounds. At that time of year, weather conditions over the North Atlantic were so unfavorable that the Hamburg Weather Service recommended changing the planned route. A southern route was possible: Lisbon, Las Palmas, Cape Verde, Brazil. Fuel for this route was quickly arranged with help from the New York-based Vacuum Oil Company. On January 31st, 1931, the Do-X flew from Lisbon to Las Palmas at an average speed of 119 miles per hour. The flight took less than 7 hours. At Las Palmas, the remote Gando Bay, 19 miles away, was chosen as the departure point for the next leg. During the takeoff run for the Cape Verde leg, the aircraft was damaged by 2 beam Cs. The Do-X was towed to Las Palmas for inspection. Repair materials were immediately dispatched from the factory. But once again, transporting the materials took about 6 weeks. Repairs were carried out where the Do-X had been towed. By April 27th, the aircraft was ready to continue. During its stay in Las Palmas, Italian Air Minister Italo Balbo, returning from South America, inspected the Do-X and proposed testing it off the coast of Africa. Fuel, lubricants, and other supplies were prepared at Villa Cisneros and Balama in West Africa. With the departure from Las Palmas for Villa Cisneros, the period of trial flights off the African coast began. After a 1-day stop at Villa Cisneros, the Do-X departed for Balama. The 932-mile flight lasted 8 hours. In Balama, the Do-X spent 3 days. The time was used for engine inspections, refueling, and scouting for a suitable takeoff area. The aircraft then flew to Boubaké, one of the islands in the Bissago archipelago. The stay there lasted 3 weeks. Little is known about this period, and the extended stay drew sharp criticism. The expedition leaders set out to determine the maximum takeoff weight for the crossing to Natal or Fernando de Noronha. Takeoff attempts at Boubaké were complicated by tropical rains. High humidity and extremely light winds made getting the heavily loaded aircraft airborne nearly impossible. On top of that, civil unrest and related censorship plagued the colony during the Do-X's stay. Weather reports came in irregularly. Communication with Germany could sometimes only be maintained through the Do-X's own radio transmitter. Direct radio contact with outside stations, bypassing Balama, was impossible due to the volatile political situation in Portuguese Guinea. By the end of May, the weather had not improved. The team decided to fly to Cape Verde with a lighter load. Temperatures there were similar, but the humidity was much lower and the winds much stronger. On May 30th, a 7-hour flight from Boubaké to Porto Praia on São Tiago was completed without incident. At Porto Praia, the Do-X expedition received a warm welcome and full support from the Aeropostale radio station staff. A government tugboat even spent days helping survey the waters around the island. On June 4th, the Do-X took off from near the French radio station at São Martinho and set course for Fernando de Noronha. After a 13-hour flight, the aircraft touched down smoothly at 2:10 in the morning on June 5th. After refueling, the flight continued that same day toward Natal and Brazil. On June 18th, the southbound journey resumed. On June 20th, the flying boat reached Rio de Janeiro. The Do-X's arrival in Brazil's capital was met with great enthusiasm from both the public and government officials. The President and the Minister of Foreign Affairs both took part in welcoming the crew. With the arrival in Rio, the 4th phase of the flight program was successfully completed. Inspections, demonstration flights with government officials, press representatives, and other VIPs, displays for naval officials, and checks of the aircraft and its engines filled the days. By early July, everything was ready for the onward flight to North America. But back in Germany, the economic crisis had worsened dramatically. The lack of funds put the remaining flights in jeopardy. Only in early August were the financial problems resolved, and flights could resume along the previously planned route. The 5th phase, the flight from Rio to New York via the West Indies, Haiti, and Cuba, was planned down to the last detail. The team arranged to work with Sindicato Condor and American Airways, which operated air services along this route. Both airlines provided airport services, radio communications, and weather reports, and handled the transport of mail and passengers. In return, the airlines received half the revenue. The economic crisis in Brazil unfortunately kept the public from booking these extraordinary flights. Advertising, largely controlled by the American airlines, mostly served their own interests. Bookings for the Do-X were often weak, with reservations coming in at the last minute. Financial difficulties also affected departure schedules. The flight from Brazil through the West Indies to North America followed the regular service routes along that corridor. Stops were also made at smaller intermediate points to pick up mail and passengers. Departure from Rio, per the flight program, took place on August 5th. The flight proceeded without incident until Para, where on August 9th, a crankshaft in one of the engines broke during takeoff. Although test flights with 11 engines showed good results, the expedition leadership, aware of an approaching hurricane in the West Indies, decided to wait for a replacement engine from Natal. The engine arrived on August 16th. On August 18th, the flight continued across the equator toward the West Indies and North America. On August 22nd, the aircraft reached Miami. With the arrival in New York on August 27th, the 7,332-mile route was complete, and a major milestone achieved. The flying boat arrived in New York in impeccable condition, later confirmed by specialists who examined the aircraft and by invited guests during private demonstration flights. By the time the aircraft reached New York, the Curtiss Conqueror engines had logged 300 hours, slightly exceeding the service life guaranteed by the manufacturer. The engines were removed and sent to Curtiss for overhaul. This gave the Do-X a 2-month pause. It was hauled ashore at Curtiss Airport, North Beach, where the entire aircraft was inspected and cleaned. What happened next, after the overhauled engines were reinstalled, depended largely on the economic situation. Still, it is hard to overstate the impact this flying boat had on the world's perception of what aviation could achieve. The experience gained from operating the Do-X laid the foundation for the further development of large aircraft. The Do-X served as a rigorous, real-world proving ground for large-scale aviation engineering, and the data it generated advanced the industry as a whole. For the first time ever, a brand-new aircraft was tested so thoroughly across different countries, climates, and seas. Flights over Europe, Africa, South America, and North America through constantly changing winds, weather, sea states, temperatures, and humidity produced a wealth of invaluable data. This information was applied to the practical operation and further development of large aircraft. Of course, sticking to a precise schedule was impossible. The primary goal was to complete the test program reliably. The Do-X flights, within the scope of those tasks, could not be compared to other long-distance flights, record-setting attempts, or regular air service. Repairs after the fire in Lisbon and the damage at Las Palmas were carried out on-site as soon as materials arrived from the factory. In neither case was the damage caused by any design flaw or flight error. The total route distance of 15,410 miles at an average flight speed of 106 miles per hour, with an average daily distance of 571 miles, was a remarkable achievement for a flying boat of this size and type. The rest of the test program was completed. Short and extended stops along the way were used to showcase the aircraft and let anyone interested inspect it. The flights completed under the Do-X test program, total distance flown, 15,422 miles. Total flight time, 146 hours. Average flight speed, 106 miles per hour. Average distance covered per flying day, 571 miles.